Thank, thank you very much, Erik, for this nice introduction, and thank you also for inviting me. It's a big pleasure um, to have here the possibility to give you some insights into our research on the SEI and thermal runaway. It's an important topic, thermal runaway, safety of batteries. We are having a lot of aging batteries. We are having a lot of new technologies and batteries, and we really want to make sure that they are safe. So this talk is going in this direction, but it's not going to a very applied level because we are going to look at the fundamentals in there. We are setting the fundamentals in the talk, so I will introduce you to that, and at the center of that is the SEI, where we are also looking at with various methods. And as you have heard, that one of the methods we are using is modeling. So we have developed several models to give you those insights which you cannot get basically, or not easily at least, from experiments. Good. So, with that, I would like to go to the first slide. So, as already said, there are a lot of batteries, numbers are rising, application areas are rising, and the question is whether they are all safe for all conditions, even if they age. The second thing is we are pressing more energy inside these cells with new materials. And the question is also there how to tailor the safety concepts of these new cells. Well, you can do experiments, you can test a lot of things, but it would be nice if you do that, what our industry has been doing in the past, also for chemical reactors, for example, to do a quantitative understanding of the processes inside, yeah, and that is very often done also with predictive modeling. So that will be a part of my talk, but not everything, because we have nice experiments which are needed to parameterize the models. Good. So with that, at the center of this stability question is very often the solid electrolyte interface. It helps that the lithium-based batteries are working at all, because the electrolyte otherwise would not be stable, as is widespread knowledge. That's a very thin layer on top of the carbon electrode, or also lithium metal, and it's extremely difficult to analyze. It's important for performance, important also for safety, as we will see later on. And structural analysis, thickness analysis is difficult to analyze, as I said. And there are a lot of factors impacting the structure, the composition, and the performance. Yeah, the solvent, depending on the solvent which you choose, you get different SEI components, for example, lithium carbonate or lithium ethylene dicarbonate. The conductive salt will give also different components, like the lithium fluoride. You might have contaminants inside there, like water. We will also look a little bit in that. Also, that is impacting the SEI, and additives are long known to be used also for batteries. They are having an impact also, and there also we will have a short look inside. And all that is, can already see that it's a complex reaction mechanisms which are interacting there, leading also to complex SEI formation. And a lot of people are working, and we are also working at trying to understand that. And yeah, one of the parts we will focus on in this talk is what is happening with this SEI if you increase the temperature 60, 70, 80 degrees. Stay tuned. So, before we go to decomposition at high temperature of this SEI, let's first have a look how the SEI is basically built. It is known that the SEI is built during the first formation, so the first charge. This charge, you go down with the potential, and at one place, if the potential is low enough, then the electrochemical reactions are triggered and the SEI is forming. We have simulated that with kinetic Monte Carlo model built from scratch already some longer time back in 2017. And here you can see how the SEI is forming basically during the first charge. And what you can see is the SEI is having here, so this potential is having here a slight plateau exactly in that area where it struggles to form a first layer. And once the layer is formed, properly, then the potential goes down further. So these are what kinetic Monte Carlo models can do. Um, you can also, I would not recommend kinetic Monte Carlo models if you go for lifetime prediction, because they cost really a lot of computational time, and they are quite complex. But for the first formation, that can be done. If you want to go for a longer time, you can go to physicochemical models like the well-known pseudo two-dimensional model from Newman, if you extend it by the SEI, for example. We have done that, and then you can parameterize the model and the SEI part of the model with, for example, impedance. As we see here, that is the anode impedance, and that has been decreasing over time. And then the question is, why has that been happening? Then the model will tell you, well, as expected. I mean, you would think if it goes down, maybe the thickness went down of the SEI, but no, the thickness increases as expected. But on the other hand, other properties of the SEI changed. For example, the conductivity, yeah, went better. So that means the composition of the SEI probably changed. The model does not tell you why, but it can just it's a diagnostic model basically. And you can see that the surface area basically increased, and that leads to this smaller cycle. I have one more teaser on the continuum level. If impedance is very powerful, but if you have various reactions at the surface, you cannot distinguish between them. For example, between plating and normal SEI response. Intercalation, there we developed this nonlinear frequency response analysis for batteries, where you put a large sinusoidal input inside and you get higher harmonic responses, yeah, the second or the third harmonic response. And we do that because electrochemical reactions are inherently nonlinear, and so if you have nonlinear responses, you can, and they are different, they can be attributed to different reactions. I can show that to you here as an example of a simulation which reproduces experiments very well. If we are charging a battery, and we are in between always doing impedance and NFIA measurements, then at one point we will get plating. You can see that here. The plating goes up at 70% state of charge. And impedance is very frequently also used to detect NFIA plating. What you can see here, it also detects it by going down in the Z, but the NFIA is even a little bit earlier, so you can basically use it's a more sensitive method to plating. Good. Okay, so that was the continuum modeling. Now we would like to look a little bit more into the SEI to understand how it's built up, that we later on can also in the second part of the talk see how that is going to be destroyed or reformed. And we go back here to kinetic Monte Carlo simulation. There's a cooperation with Perla Balbuena from Texas A&M. So this is really a predictive kinetic Monte Carlo model, which we are again operated from scratch. Perla Balbuena showed us the mechanisms for the SEI decomposition of EC, that is this here, in combination with lithium. We have also LiPF6 in here. So these are the ions, as you can see over here. And classical molecular modeling can only go to picoseconds or something like that. So very small seconds, that is not helping, also not in the size to get the real SEI. So that's where we came up with the KMC, and we fed the parameters for energy parameters for Perla inside. And here you can see now what happens in the model if you let it run. After 1 nanosecond, some things are building up, then more, and finally you get this nice layer of SEI after already 1 microsecond. What you can see is it's indeed a layered structure. LEF comes first and the lithium carbonate, and that is basically due to the lithium fluoride is quite fast reacting, and because LiPF6 is a low concentration, yeah, it's not growing too fast, but the layer is not dense yet. The EC can penetrate through there, much higher concentration, right? It's a solvent. It goes through and builds the lithium carbonate below over there until it is also consumed and also, yeah, basically. And then the LEF layer is then also dense. So at that point, the formation is done basically. And what we can, yeah, learn from that is, yeah, okay, there is this interaction of these two species leading to the layer of LEF and lithium carbonate. Good. So, but then there were reports in the literature saying, okay, but we have mosaic type structures. Others were saying we have layered structures, and they all had a little bit different conditions. So we said we play around now with the concentration here. Let's, for example, increase the lithium fluoride, the concentration of the salt. What you then will see is that if you increase the concentration of the salt, going from 1 to 4 molar, you have a faster layer of lithium fluoride building and a thicker layer, and that is getting dense faster, less EC can penetrate, and therefore you have a thinner layer. But you not only have a thinner layer, you are also having a more mosaic type structure. Yeah, so the question is the SEI layered or mosaic type? Will depend on the conditions also where you do the experiment. And that means also you could probably influence it if you are first time forming the SEI basically. You can also see that here that the 4 molar is building the layer much significantly faster than the 1 molar, yeah, and that this is a thicker layer over there. The same thing you can play also around with EC DMC. You can dilute it basically or use other salts. But I don't go into detail there, but I would like to show you something else, namely additives. Additives are used to have a better formation of the SEI. Very often VC is used, vinylene carbonate. And then we said we would like to check that also whether that works. So VC is if you put it inside, it will do polymerization. Polymerization is also a chemical propagation reaction. So we said, okay, we will extend the model. It was quite some work. But then we got that inside. Again, Perla's parameters, and then we were a little bit disappointed because what we saw is basically the layer is the same without VC or with VC, just that we got a little bit dimers and trimers after 1 microsecond. Okay, so that means the VC polymerization is quite slow and it's not really happening at these timescales. Then the question is, will it happen at higher timescales? And the answer is yes. And that is also, yeah, where we went to 1, 2, 3 seconds, and we were able to see here the polymerization, yeah, poly VC, poly EC, VC, basically cross polymerization happening. So that gives indeed a quite large thickness. Yeah, in reality, that might stop earlier if you have basically some radical scavengers in there, then it will stop earlier, but we don't have them in the model. So yeah, we can't really say when it stops, but what we can say is that we have still a kind of layered structure over here. So, and the VC is a slower reaction, taking some time. And the second thing is this polymerization itself does not require additional lithium. So you are kind of shielding the SEI, shielding the lithium from further electrolyte without consuming lithium. Yeah, so and that is interesting. What you see here on the right side is also that these polymers at the end become quite long. Yeah, if they don't find a radical for recombination, basically. So how does VC seem to work? That's what the what we suggest. It consumes no lithium. It stabilizes the SEI by a nice mechanically probably more stable layer and preventing any dissolution. So so that was for the SEI. We can now see they might have different structures, different thicknesses, compositions. We will use that later on in the thermal runaway analysis coming soon. But before that, I just want to say you can do the same thing also with other batteries. We did that here in the Cluster of Excellence Polis together with Axel Groß. So there for sodium-ion batteries, so on hard carbon, the SEI, we identified together with the group of Axel the reaction mechanism. We got the reaction parameters from them, and then we set up our model, and here is what you can see. So if you charge for the first time, and I think that is 0.25 C, yeah, so it's a long time scale, we can see how from one SOC to the other, this SEI is building up. In this case, we didn't see a layered structure. We saw mostly sodium carbonate. That was a little bit surprising for us because we thought also we would see NEF because it's in literature, it is reported in experiments, but our model clearly says that this is with the things which we have inside, it's not going to happen. So so NAPF6 is too stable to decompose with the reactions we have inside. But we have been showing now, but it's not yet finished our results, so I can't show them today, that we have a pathway, a new pathway identified where we get also the NAF. Good, and then you can again play around there with the composition of the SEI. Good. That brings us to okay. Yeah, okay. That's the last point I wanted to make here. What we saw also over there is that the SEI is probably dissolving, and that would mean we yeah, probably need also some additives there, but that is also ongoing work. Watch out with what will come in the future. So, but that will now bring me to the second part. So, self-heating in lithium-ion batteries and the SEI. Self-heating is the first part which happens before thermal runaway, where the SEI basically heats itself. Self-heating, that's what the name says. So, if we look inside, there are some accidents around where this has happened. And this is, for example, a Tesla burning on the left side with the batteries. And there was no crash, nothing before. It was just some when it was heating, accelerating heating, and then the car told the driver to stop by and get out. And then it was going into flames. So that is definitely something which we want to prevent. A lot of people are also now, or more and more people are now working on this in this area also. And most of the focus is then on the thermal runaway. But we are more interested in the area before, because the question is what triggers this kind of self-heating also. It is mostly chemical reactions in the cell which are exothermic or endothermic, and many of them stem from the SEI basically. And that's also shown in this work over here from Feng et al., where you see the SEI decomposition and reformation is coming early. And then only around something like 160 degrees and above, you will really see the cathode coming in. So that means the SEI plays a crucial role during the initial phase, as it causes also the self-heating. And well, we wanted to know what is actually happening there. How is this SEI decomposing or reforming to understand basically how to design a better cell. So what people in literature or in the field have been doing frequently is accelerating rate calorimetry. So what do you do there? You heat the cell and then you wait. Does it heat up itself? No, if it doesn't heat, then you heat again until a certain temperature. You stop heating and you look, nothing is happening. Okay. Then you heat again, and at one point, it is the processes inside there are so exothermic or more exothermic than is transported away that you have a slow exotherm phase, so self-heating phase until you get to the fast runaway. So this is the critical phase, and that frequently happens below 120 degrees. So what we need for that, for a model to reproduce that, is clearly a model which has this SEI growth decomposition inside, which has of the SEI at higher temperatures of the cathode, but also of the electrolyte. Be aware that the cathode reactions are mostly actually 150 degrees higher. What else do we need? Each of these reactions, if you have formulated them, you can check whether they're exothermic or endothermic. So that was the wrong direction. So we set up a model where all the reactions are inside, including whether they generate or consume heat. But this is not everything, because you also might have phase change in there. Yeah, some gases are evolving, some other gases will evaporate. Yeah, and we put all of that inside, including the ARC. So with that, we looked for experiments, and that was not so easy because most of the cells nowadays, if you have ready-made cells, they are having additives. So as you have seen from the slides before, additives are having a different reaction mechanism, even more complex than what the zoo already, which we see in front of us. So we looked for a little bit a cell or experiments which did not have that, and we had to go back quite some time to find one. And then we parameterized our models to that. Yeah, this was only, this is no NMC, that was still a lithium cobalt oxide cell, basically, with carbon on the other side. And we were then able to reproduce what you can see here, this self-heating phase and the other performance here. And you can see, you look at the time scale from 10 to 20 hours. So it takes 20 hours, so 10 hours. So there's really a fight happening in the battery until this thing dashes off. And now you have the model. The model can reproduce that. We can look inside. Oop, or wrong direction again. So what we see. First of all, we go higher with the temperature. We have endothermic reactions, so consuming energy consuming reactions. So they even cool the cell, and that is the salt decomposition, the HF production, basically more from the electrolytes. But on the other side, we have here the organic SEI decomposition. This is LEDC, and the inorganic is lithium carbonate. Kicking in one after another. And once they are starting, they are slower starters, but they are producing heat. And once at one place, which is approximately around here, we have more heat produced than consumed, and we are exceeding the threshold, and the cell heats and heats and heats. And then also we have the SOA formation. So once it is decomposed, new lithium carbonate and LEDC is produced. So that is a circle which the salt basically cannot win. Yeah. Good. So that is now the insight which the model is giving, and now we can have a little bit a deeper look inside. One thing I noticed I mentioned before is we have electrolyte. Electrolyte might evaporate. So the question we ask ourselves at the beginning: does the electrolyte, the solvent, evaporate? And what happens if a solvent evaporates? It gets colder. So we Florian Barkes here, in my former PhD student, he had a look what happens if you heat the cell with the solvent. Well, first of all, things will evaporate, yeah, a little bit. So and also gases will produce. So the volume of the cell will go bigger, yeah, if you have a pouch cell. But at one place, pressure will build up. And at this place, what happens when the pressure builds up is the boiling point is also going up. So the boiling point increase was similar to the temperature increase, so that you will basically not, during the heating, self-heating phase, you are not reaching the boiling point of the solvent. And that means we have no evaporative cooling effect. That might be at the end, that might be used in batteries on purpose, this kind of evaporative effect, if manufacturers would be able to use the effect, right? But that you need to design your batteries for that. There are a lot of impacting factors for the pressure buildup also. So the question is, have you used argon during the build-up as pad gas? Then you will get less pressure than if you have, for example, used CO2, because the CO2 is going to dissolve in the solvent, and if you heat up, the CO2 evaporates and increases the pressure, as you can see here. You can also think about is it a linear or cyclic carbonate which you have as a solvent, and that will also change the phase change. And finally, yeah, the reactions, yeah, will come into place also. So solvent composition, conductive salt, the composition under gassing conditions. But what we also found, and you can see that also here from the left, is that the casing will have an important effect also on the pressure buildup in the cell. And don't forget, so pressure buildup will basically prevent the evaporation, but at one place you might have the current interrupt and the venting, and then that is definitely also not something you want to have. Good. Anyway, so we let's go further with that. The pressure effect has been looked on. What can we look at else? If you look at here, the reaction network, we have the electrolyte here, the SEI, exothermic reactions in red, endothermic in blue. And you can see here also the water, the salt decomposition, which we have here, which is endothermic, LEDC, and the lithium carbonate, clearly exothermic. But you also have here some connections, basically. The question is now, how do we impact this thermal runaway behavior, or the self-heating? Yeah, is an older or thicker SEI or an older SEI, is that better or worse for the stability? Yeah. Well, you change the amount of these guys, maybe also the ratio of them, so that might impact. On the other hand, here the water also plays a clear role, yeah, but it has some endothermic and some exothermic paths here, yeah. So how does that play in? And do I have to maybe go for more drier process during preparation of the electrodes of the cell, basically? Let's go through that. we start with the SEI composition and thickness. If we now say we don't have a 40% LEDC and then about 50% lithium carbonate, but we go to more organic SEI, so more organic SEI would mean you have a more reactive SEI, and indeed you can see that here that starts early. Yeah, the thermal runaway starts at 98 degrees instead of, if you have no LEDC inside, 127. So that is already a gap of 30%. And you can see that here that this is especially coming from the LEDC decomposition, which is triggering this early onset. On the other hand, the thickness. The thickness is also the thickness is less straightforward. More thickness means more reactants, but less thickness means you might reform the SEI faster. And what we saw is what the model predicts here is that a thinner SEI is actually worse because it's reforming faster, and that is also an exothermic reactions. So if we would assume, if we assumed that aged cell is thicker and more inorganic, I don't want to make any conclusions how the SEI later look like, but just assume it is thicker and more inorganic, then this battery would be safer. And yeah, well, the question is how aged batteries look like if they are thicker and more inorganic. And we have just the SEI as a focus, then that would be safer. Good. Let's look at water. Water was interestingly much less or the runaway behavior was much less sensitive to water content. Whether so we changed here up to 505 ppm, yeah, and then we got a little bit earlier onset of water than here, than here, but it's less strong. So the question is, what has happened there? Well, water we have seen, theoretically, we would have more salt decomposition, so it should cool. It is also cooling, but that is only the first phase here, which is cooling it. But at the time when the heating here, when the self-heating comes, these reactions here are also playing inside. So we have formed more lithium hydroxide here, and this is also an exothermic decomposition, which you can see here, and that is kind of triggering the thermal runaway then a little bit earlier. Good. So still we did not see much of a difference between the two other points here and the 260 ppm. That is the water which we calculated is in there if you do a medium dry process from here the publication of Arno Quade. So that was the water impurities. Now we have seen the impact of water on the thermal runaway. We have seen the impact of aging, etc. And all of that has been parameterized more or less at the beginning only. All this reaction zoo to one ARC. That is left us with the question, how quantitative are we really? Do we have the right network? You have a different network, something else might come out. And then we said, okay, we should go somewhere and get a little bit. What do they produce? They produce heat. That's what you measure with ARC, but they also produce all these gases here. So if we are able to measure these gases during heating, then we might get a better, a more reliable identification of the network. And that's what we have built up in the last years. We have here a cell in the middle. and it has a very small capillary here, and here bypass of argon. So if you're heating that cell, everything which evaporates, all the gases, they will flow out here, and we can measure them. And then the cell can be heated. Yeah, you can see here we can go up to 130 degrees, hold it, and then go down, and then you see a zoo of all the reactions here kicking in: CO2, POF, CO, ethene, hydrogen, all coming in. So that is actually a good base to understand uh, or to identify the reaction mechanisms, which reaction starts at which temperature here. Yeah, and yeah, you will see it's still a little bit complicated, but I can show you something what we found out with this technique. The first thing which we did, we set up and tested various materials, and then we found something we were a little bit astonished, namely that if we use different separators, we get different gases. All separators which we were using in the cell, and here you see the materials over there, all the separators were supposed to be stable below 130 degrees. I guess they are if you don't put them in a battery. Right? So we have glass fiber PET, PP, and PTFE. So, and what we can see is for PP and PTFE, the pattern looks same: CO2 and a little bit here of methane, etc., coming in. But for the PET, we got huge amounts of CO2, and also we got hydrogen over here. We got also hydrogen here. Also here a lot of POF3. So, and in addition, what the PDT aluminum oxide separator was not stable at all anymore. So and we were only heating to 130 degrees. All the other ones were stable. So conclusion: they are not stable. These two guys here are not stable in the battery, and there has to be a kind of reaction. And Lars Bloibaum, my PhD student at that point, proposed this mechanism here, that the HF, which we are anyway producing, that might react with aluminum oxide for the PET or with the glass fibers or the borosilicates here and form water. The water can go to hydrogen. Here's a hydrogen coming, and it can produce more HF, basically. So that is a possibility, and the HF can also here produce some more CO2. So separators are not as stable as you want, so one has to be a little bit careful with that. So, but we are now using only these guys over here. Next thing, what we have seen is different SEI, or what we have prognosed before is different SEI. Formation will and VC will have different SEI composition. So let's have a look there. What we found, what Leon found in his work is if you do a formation, then with higher C rates, you get more CO during the formation, and you get, also if you use less VC, you get also a little bit more gases, basically. So the reaction, but what, what I have to say is the ethene, which you have there, that most likely comes from the EC, which produce lithium carbonate, or the LEDC, which you have seen before. The CO, that was already a new reaction which we did not have in our modeling so far. We found that in literature also. It is produced when EC decomposes to CO and LEG. So we have a new SEI component over here, which is produced more for higher C rates. And this reaction needs a little bit more overpotential. That's why you basically see that over here. So now let's look what happens if you then heat this up. Will that have an impact? And the answer is yes. And I want you to focus just on these two curves over here, that is the gas evolution for C/10, and this is one for 1C. And what you can see here for the C/10, you get a lot of POF, but little hydrogen. And for this one, you get a lot of hydrogen, yeah, and little POF, basically. So the formation, yeah, impacts definitely the safety, yeah. Um, Good. So, there again, we were thinking about how that works, and now comes into play what we saw before. So this LEG, which you have there, at high temperatures, that might react with HF and produce this EG, ethylene glycol, and on the way back, it produces the hydrogen, which we see here, which we see very little, much less here. Yeah. And why do we see here then more POF and here little? Because the HF is basically, that is a circle here, which would at the end produce more POF3. And if you take the HF out of the cycle, which you have here, you produce less POF3. So the LEG acts basically as a scavenger. So that was, we can already see that SEI composition will have an impact on the reactions taking place, on the amount of gases, and probably therefore also on safety. Now we wanted to model that, and we tried first with the full complexity, but that was a little bit too many parameters to determine. That's why after some time we decided we will go back. So Jorge, my PhD student, then just took pure electrolytes and heated it, because that's already sufficiently complex with some reactions, and I can show you what we did there. So we did OEMS measurements again, and well, the whole OMS measurement, including the transfer line where you can have further reactions, is modeled in there. And we have different scenarios. First, EC DMC, as you saw before, but then we said also, well, let's just have a look at DMC with salt, and then DMC only. DMC only gave us already the first enlightenment, because DMC only, it goes up and it goes down. Why does it go down? Because this is an open cell now, and the cell is going to dry out. So it goes up because temperature goes up, and then it stays in there with a certain constant evaporation rate, but at one place, yeah, the DMC is too little, yeah, and then it will go down again. And so we have reproduced that, and that is important to keep and understand also what is happening in the cell to interpret it later. So what happens now if you put the salt inside? With and without EC, this is shown here. We get DMC again going up, going down. You know, understand that. We get a crazy POF3 thing. It goes up, goes down, it goes up, and goes down. So we have at least two reactions, I guess, in there which are interacting. And here I have to say the gray curves are the experiments. So I'm sorry that you don't see them too much, but yeah. So we get also CO2 going up, going down, and CH3F also going up, going down. CH3F obviously will come from a dimethyl carbonate, so there's a methyl group over there. Yeah. What we see, whether you have EC or EC DMC or only DMC, the progression in all these cases is similar, just the magnitude is different. Yeah. But that also means you get different composition of your gases inside the cell, whether you have DMC or DMC EC. Yeah. And the DMC, the EC is suppressing the PO3 and this thing over there, but it's increasing the CO2. Keep that in mind for a little bit later. So we were thinking long how to model that, and Jorge came up with this nice mechanism over here. Sorry, it's a little bit colorful, but that will help us to go further. So we have three POF3 production mechanisms: LEPF6 hydrolysis, PF5 hydrolysis, and then we have this species over here, the ester, which can react back to PO3. And on the other hand, we have three decomposition reactions of POF3, ones with DMC, ones with EC, and one hydrolysis again. And we have, in addition, this EC over here. So, yeah, so that means we have a zoo, and we can now go on and look at what is really happening here. You can see all the different reactions over here. The reaction rates, they depend on temperature, because obviously they will get faster with temperature, but they also have a different slopes. The hydrolysis is faster, yeah, but at the end we have less water. That's what you see here. That's what you see here. The water goes down fast, so that means the POF3 can only come in the first phase from the hydrolysis. And the other step, okay, the other step, which is basically more important, giving the second peak, is this, now I go back, this back reaction here, this kind of loop which we have implemented there. Good. So you can also see that here, this POF2OCl3 degradation, it goes up, it goes down, and partly it goes even up again. And we have the polymerization of the EC also going in there. So we were very happy that we were able to reproduce that, and we are now going to go for a further a full cell model with that. Before I think I have 1 or 2 minutes left. I would like to show you our recent results, because unfortunately it gets a little bit more complicated. So we prognosed polymerization in experiment. We were also seeing polymerization indeed. More water led more polymerization, but also lower potentials. And we have there also an interesting mechanism where we think that this EG, which we identified, yeah, that triggers the polymerization basically. And if you look there, you will also see that if you have a lower potential, you are or if you have a higher potential, that is this one here, you have a lower anode potential, more of this classical CO and ethene production, but less of the basically production of the polymer basically. That's why we don't see that over there. And finally, to make it a little bit more complicated even, we found some crosstalk and some acids on the cathode side during the reactions, and also there is a suggested mechanism over here with a complex basically a cycle of water. So we have an oxidation of this EG at the over here at the cathode, which again produces water. So that was just a teaser at the end. That will all make it a little bit more complex to try to put that all in the model, but we will see. We are hopeful that we will squeeze that in the future. What I hope to have shown you with the presentation is that there's a lot happening in the SEI formation, but also in the degradation, and our models and the OMS give some nice insight inside there. Also into the self-heating, the exchange of the exothermic and endothermic reactions. We found some new species, polymerization. And my personal vision is that we kind of trace that down into the model so that we can design better cells and operating conditions to prevent the self-heating. And with that, I would like to conclude my talk. I hope you had a nice view and you liked that. I would like to thank my PhD students over here, which contributed very nicely, that our collaboration partners here, these guys here for funding, and thank you very much for your attention. I'm looking forward to questions.